Hello, today we're going to understand how convolution 2D kernel works, and at the end, we will answer some questions, and in part B, we're going to train a given neural network and then respond to some questions. First, what we do is we import the necessary packages and libraries, and then we're getting the image from the URL, and then visualizing it, and then we are saving the image into the RAM, opening it, and then transforming the image into 3D array, uh, which will contain values from 0 to 255, 0 being black and 255 being white. And this is what the image looks like. It's a very nice car. And then we're going to print the array shape. Um, Basically, what it does is that the second and the third parts compares the values of the different color channels in the image of the array, and then the shape represents height, width, and the number of color channels in this image. We have 3 color channels, and over here we're selecting all the values along the height and width dimension, and then we're just choosing the first color channels, and then we are doing the comparison because we want to check whether the image has a dominant color channel or not. And the print statement returns both false. That means corresponding color channels of the input are not equal. And then we're going to save the color channel into 0 into the our image array, and then we print it, and this is what it looks like. Basically, we're extracting the and displaying the first color channel of the image, so we can simplify the image and reduce the dimensionality of the data. And this is what it looks like. In an array, we're choosing height and width, and this is what the array looks like. And now we're going to work with convolution 2D kernels. Over here, we're going to create a padded array. We're adding 2 additional rows and columns of the each dimensions, and then we are populating it with zeros that are the end and the beginning of it, and then we're creating an array, new array that is 2 rows and 2 columns larger than the original, and then we're creating a kernel that is 3 by 3, and then we're creating an output array. It fills it with zeros, and it's the same shape of our input image array, which was the card that we have. And then we're comparing the both arrays, and here we have 2 additional extra rows and columns over here. We do this to ensure that the the edges of the input image are taken into account when applying the convolutional operation. And then we are applying the kernel to the array values. What this does is basically the code implements a simple 2D convolution operation with a 3 by 3 kernel on a grayscale image. It iterates over every pixel in the padded array, and then performs the operation of the convolution, and it results in a filtered output. And basically this is what we get. And over here we have a standard convolution. We are creating a function that will be called if the array results in a value that can be a negative or greater than 255, and then we're applying our convolution kernel to an image, and we're returning the 2D grayscale item, and then we're filtering that, and then printing it out as a numpy array. And now we're going to the line detection. So we're creating a kernel that detects the horizontal lines, and then we're going to apply the kernel to the image, and then once we plot the resulting image, this is what we get. We can see that the horizontal lines of the car are looking sharper than the rest of it, and some lines look stronger than and like sharper than uh, other parts of the car. This prints out the horizontal edges or lines. And first question, based on the kernels represent on the above image, now we're going to create the same one, but it's going to detect 45-degree lines using convolution. What we do is we get our kernel to detect 45-degree lines. This is basically what it looks like in our array. And then we apply our kernel to the image, and we plot the result, and this is what it looks like. We can see that the lines that are closer to 45 degrees are sharper, as we can see over here by the tire, over here by the door, the lights. And we're going to do the same, but with 135-degree lines. And this is the kernel array dimension, and we're going to apply the kernel to the image, and we'll plot the result, and this is what it looks like. um, it does look somewhat similar, but there are differences. For example, the lights, we can see the difference. And we're going to the edge detection. The question 2 is we're going to apply kernels to our image and plot the output. And this is our first edge kernel. This is what it looks like. And we are importing the necessary image pre-processing, and we're applying it to our edge kernel 1, and we're plotting the image, and this is what it looks like. You can see that some lines are sharp, and we're going to do the edge kernel 2. This is basically what it looks like, and we apply it to the kernel, and we plot the result, and this is what it looks like. This is the difference. This has stronger lines, sharper. And we do the edge kernel 3, and we apply the kernel and then plot the result, and this is what it looks like. Everything is more stronger and sharper. And the part B is we import necessary libraries and packages, and we prepare our data set. We load our data set into train images, train labels, test images, and test labels, and then we save them into one hot encode target values. And we are converting our integers into floats, and then we normalize our target range to between zeros and ones. We divide it by 255. Um, this is used to help pre-process the image and the data. It improves the performance significantly. And then we are building our neural network model. We're creating the model. We're using 3 by 3 because we have 3 channels. We're keeping the padding same to ensure that the output has the same height and width dimensions as the input. We're choosing ReLU. It's a common one for convolution neural network, and then we're choosing our kernel constraint to 3. It's for kernel weight, and like we're choosing the maximum kernel weight. This helps prevent overfitting, and we have the max polling 2D layer. This performs a 2 by 2 polling window to reduce the spatial dimensions of the output from the previous layer by 2. And then we're flattening it. And then we're adding a dense layer of 128 with a ReLU activation function. And then we're choosing the last layer as 10 units because there are 10 classes in our dataset, and we're choosing the activation function as softmax. And then we compile our model with Adam Optimizer and categorical cross entropy because we're doing a multi-class classification problem, and we want our metrics to set to accuracy. And then we display our summary of the model, and then this is the total parameters we have, and we don't have any non-trainable parameters, which is great. And we're going to see the custom callback class for logging. First, we create a custom class. We're going to call this during the training. What it does is that basically if the number of epoch is a multiple of 5, it prints out the method, and it gives us the accuracy and the accuracy of the train and the value that we achieve. And then we're instantiating our custom callback, and then we're training the network now. We're training the network with our train images and train labels. We choose epochs as 50 and our batch size is 256. We're going with verbose 0, and our validation data is test images and test labels. And our callback is our custom callback class that we've defined. We're setting the batch size to 256 because this is the number of samples to be processed in each batch during training, and we're setting verbose to 0 because we don't want to display any output, and our validation data and labels used for evaluating the model after each epoch of training. And with our callbacks, custom callback, we're printing in every 5 multiples of 5 epochs, and this is what we get. Basically, this is what it looks like, increases over time. And then we're going to plot the result. We're going to define a function to plot the result. And now we're defining what we want in our plot, and this is what we get once we result it. You can see that the training accuracy increases. However, validation accuracy stops at some point after 10 epochs, and this may be because we have a little overfitting. And we're going to answer some questions now. Um, well, did the network present sign of overfitting? If so, in which epoch? Yes, there is an overfitting, and it starts after epoch 10. Like right around here, we can see that it just starts improving, and we're we, they want, and then we're going to write down the number of layers in this model. Uh, and there are 4 layers: convolution layer, the flattened, dense, and max polling layer. And if you were to briefly explain what those layers are, convolutional layer is for extracting high-level features from the input image. We use the flattened layer for converting the output to 1D vector. Dense layer transforms the features and produce a probability distribution over the classes. And max pollen layer reduces the spatial dimensions in our array. And now we're going to add one or more convolutional layers to our model, and then we're going to run it again. So over here, I used the same one that we had before, and I added another convolutional layer. And then we compile our new model with Adam and categorical cross entropy and accuracy. And 50 epochs, same batch size, same verbose, everything same. And this is what it looks like after after our training. And we can, once we plot it, we can see that how our training accuracy increases and improves at some point. And we can see how our validation accuracy also improves, and then just stops at some point because I guess it's learning how to do it. And we're going to compare the results and describe the differences by adding another convolutional layer. Well, the model achieved higher accuracy on training and validation compared to the first model. This means that the additional layer is helping to improve model's performance, and we can actually see a drastic change if we look over it. Basically, it's just like learns and then says, I'm sure whatever you're giving me." And we're going to add a dropout layer to our model, and we're going to run it. So basically, I have the convolutional layer max polling 2D, and I have the dropout set to 0.2. What it does is basically in dropout, we randomly set a fraction of input units to 0 during training. This reduces the effect of overfitting, and it improves the model's generalization ability. And we compile our new model, and then we train it with exactly the same, and this is what it looks like. And then we plot it, and this is what we get. It improves over time. Okay, so what is the purpose of a dropout layer and how it works? Basically, the purpose of a dropout layer is to prevent overfitting by randomly selecting some of the neurons in the previous layer, and we drop them out during training. This forces the network to learn more generalized features instead of going through what it already knows. So it doesn't follow its own steps. It tries to find new ways to the new solution to the problem. Basically, with each iteration, the dropout layer randomly just sets a percentage of neurons to zero in the previous layer, and this helps with preventing overfitting. And now we're going to make any modification in our hyperparameters to improve the model's accuracy than the previous one. And over here, I added one more convolutional layer and another max pollen and then a dropout. And once we compile our new model, this is basically what it looks like. Much improved and better validation accuracy. And that's all. Thank you.